All right, so here's where we left off last time. We've been talking about the fundamental theorem of line integrals, and we've been talking about path independence, and of course those are closely connected ideas. They both apply to gradients, specifically, right? And of course now the fundamental theorem of line integrals, if you're going to use the fundamental theorem of line integrals, not only does your vector field have to be a gradient, but you have to be able to find the anti-gradient, right? So that's what we're going to talk about now. Kind of swept that under the rug. Previously, I just kind of pulled the anti-gradient out of thin air in the example that I did. So where did I get that from? And more importantly, how are y'all going to find anti-gradients yourselves? So here's the big idea. If your vector field is in fact a gradient, look at the coordinates. Right? And specifically what we see here is that each one of the coordinates of your vector field is one of your partial derivatives for the function that you're looking at. Right? So P, for example, is the x partial of f. Okay. All right. Well, here's the thing. If P is the x partial of f, then that means f is the x antipartial of P. That's just what an antipartial is, right? And so now likewise, Q being the y partial means that f is the y antipartial of Q, et cetera, for the other coordinates. Okay, so it's tempting to say that this is what we need to do, that I need to take these three antipartials and I need them all to be equal, and whatever that might be that they're equal to is your anti-gradient, and this is not quite good enough. So here's what you have to also consider, and that is that when you say that f is the x antipartial of P, keep in mind there's actually a bunch of antipartials, right? So which one? When we write this down, we tend to just kind of write it down and then find one and declare victory, right? Y'all will remember from single variable calculus that you have to note the many different possible antiderivative by saying plus c. Well, what we have here is a function which I'm going to be looking at the x partial of. If I were to add a constant to this f, that wouldn't change the x partial. Whenever I add a constant, the x partial is still P. But more than that this time, because we're taking an x partial, not only do constants not make any difference, any function that doesn't have any x's in it also will have x partial equal to 0 and will not make any difference. Right? So basically, for analogous reasons, then not only can f be the antipartial that you find, it could be that antipartial plus any possible function of y and z. Perfectly fine. Okay, so when I say that f has to equal to three different things, it's just a little bit misleading, I think, to say that f has to equal to that and that and that. You might pick the wrong ones. What f actually has to be equal to is that and that and that, where these C1, C2, and C3 can be any functions. By the way, just for terminology, C1, C2, C3, we call these partial constants, which I think makes sense. Okay, so let's see this in action. Here is a vector field for which I want to find an anti-gradient. Let's apply the process that we just noted. So I'm going to take my P and do an x partial of it. X antipartial. I'm going to take my Q and do a y antipartial. I'm going to take my R and do a z antipartial. And again, just, the easy calculations with antiderivatives, and you get these functions right here. But again, you're picking arbitrary, no particularly good reason, arbitrary choices here that you don't have to make and therefore shouldn't make. So don't forget that you may and therefore must consider the possible partial constant functions that you can add in there. Okay, so how does that play out? What I need then, in order to find an anti-gradient, I need for the function I'm looking for to equal to all three of these things. At a quick glance, they don't look the same, right? You see these first two have an x squared y term. This third one does not have a visible x squared y term. Seems like they're different. But keep in mind, we do have the flexibility to put whatever we might need to into here. And so, in fact, I would propose that we can, in fact, make all three of these expressions have an x squared y term just by choosing to have this C3 function be x squared y. It works. Right. And then let's see here. Let me get my colors straightened out there. Let's see here. What about the xz? I see xz's there and there. And you know what? Xz could be that function, couldn't it? Right now, all three expressions have xz in them. And then lastly, we have a minus yz squared there. And sure enough, it could be that C1 function as well. So conveniently, having chosen these partial constants as indicated, all three of these expressions are the same. So there is a function that's equal to all three of these things. That's it. Yeah.
Wouldn't you also need a plus C in the final function?
Oh, yeah, you could. You could, yeah. Typically when we notice I say an f, right? So my goal here is not to find the general antigradient. My goal is to find, I'm not trying to find the general antigradient. I'm just trying to find an antigradient. Yeah. So when you're only asked to find one, this is sufficient. Yeah. Good. Okay. Now here's a concerning thought. And you look at the question here. We had this vector field given, and we have a game that we can play here. You go through and play little mix and match games, right? Trying to get everything to line up. And you play the game, and you win the game, and that's your antigradient. Well, that's okay, because in this case, we knew there was an antigradient. You can compute the curl right off the bat. You can see that you get 0. Easy partial derivatives. There's nothing to it. So you know that there is an antigradient to find. Here's the worry. What if there is no antigradient to find, and then I find one? Wouldn't that be distressing, right? That'd be a problem. Let's worry about the possibility that might happen. Now, of course, it's not. But how does this play out, right? How does our game conclude when there is no antigradient to find? So let's consider this vector field right here. Let me remind you, we've seen that vector field before several times, including last time, in which we noted that we can compute Green's operator. We don't get 0. Therefore, there is no antigradient to find. So how does the game go down in trying to find something that doesn't exist? And here's what you end up with. You take the appropriate anti-partials and you add your partial constants, and I need these two things to equal to each other. So try to play that game, right? Try to think through and find some function of only y, some function of only x that makes these two things equal to each other, and you're going to give up pretty quickly, right? There's just no way to do it. Not going to happen. Okay, so that's how this is going to work. If there is no antigradient to find, then the game will be an unfair, unwinnable game. Okay.
Just a quick question.
Yeah.
Could you use the fact that you can't find an f equal to both as a reasoning to say that green of f is equal? There is not.
I mean the problem there is you're kind of putting a certain amount of weight on your own ability to play the game, so it could be that there is no way to win the game, or it could be that you're just not very good at the game. You know what I mean? Nothing personal, right? So I hear where you're coming from. If you can show that there is no way to win the game, that'd be a compelling argument. But how would you show that? And it can be done, but it's honestly just much easier to just go ahead and compute grids on there. Yeah. Okay, we're done with Chapter 6. Moving along, Chapter 7. So Chapter 7, just big picture here. We're going to be basically developing three-dimensional ideas analogous to the two-dimensional stuff that we've been talking about. Right? So we've talked about Green's theorem, for example. Specifically, Green's theorem is an intrinsically two-dimensional theorem. Right? Green's theorem is only in two dimensions. There's also, in two dimensions, fundamental theorem of line integrals, path independence. Now, these ideas extend to three dimensions, no problem. In some sense, we've already done that. But what's the three-dimensional version of Green's theorem, or is there one? What's the three-dimensional version of the alternative Green's theorem? The two-dimensional divergence theorem about boundary flux. What's the three-dimensional version of that? So there's a lot that goes into this. The good news short answer is that we are going to find three-dimensional versions of these theorems. And they work out just fine, and I would almost go so far as to say they're exactly what you think they'd be. They're certainly highly analogous, right? So a lot of good news coming down the road. But we do need to develop some machinery. There's some tools that we're going to need to make sense out of all of that. And we're going to start here with the idea of a parametric surface. It's a really big deal in what we're going to be doing in Chapter 7, just for analogy purposes, right? So, what was the Chapter 6 version of this? It's parametric curves. Remember, we did a ton of stuff with parametric curves in Chapter 6, right? That's how you define vector line integrals in the first place. It's by parametrizing the curve and then pulling back through the parametrization. Okay, so we need to develop a parametric surface idea. The good news, it is totally analogous to parametric curve. A parametric surface is positioned as a function of two parameters compared to a parametric curve, which is positioned in terms of one parameter. Right, so it's a really natural extension of the same idea. Okay. Here's an example we've already seen. You can go back to section 1.5. In fact, I think there was a homework exercise, if I remember correctly, that talked about this. And so let's suppose we're interested in a plane, and for example, like so, and I want to be able to talk about points in that plane. I want to be able to I want an expression that will spit out points that are on this plane. How am I going to generate these points? And the big idea is to notice that, if we're going to do this, we're going to need some given point in the plane to talk about. Then we're also going to need some direction vectors, V1 and V2, just to be able to make sense out of what plane are we even discussing, right? I'm going to need a point to kind of nail down where the plane starts, and then two direction vectors to help me understand how the plane is kind of sitting. Which direction is it kind of facing, if you will? How is it oriented in space, you might say? Okay. All right, so with that noted, I can get to any other point in the plane as desired just by starting at my given point and by going some amount in the V1 direction. Now, that might not be exactly V1, right? So V1 is a fixed vector. It might be too short. Maybe I want to go farther, but in that same V1 direction. So I give myself this scaling factor called S, right? And then also, to some extent, in the V2 direction. So, V2 might not be long enough. Maybe I want to go more in that direction. So T here is going to be our scaling factor that helps me go as far as I want in the V2 direction. Okay, and notice these add, right? So if I start at this point and I go some amount in the V1 direction, some amount in the V2 direction, I get to another point in the plane. Furthermore, whatever point I want to get to, I just need to go appropriately far in the V1 direction and appropriately far in the V2 direction. So there you go. we in fact have now a parameterization, and you'll notice specifically that I have points on the plane entirely determined now by two parameters. I missed the thing, S and T, like that. That's a nice little construction. This is our first parametric surface. This is a parametric plane. Everybody okay? Everybody on board? Okay, one little bit of bad news. This is disappointing, but oh well. That's how life is sometimes. You notice that because you have two parameters, you can't use this little convenient crutch that we used when we were talking about parametric curves, about thinking of your parameter as being time. Right? That was really useful thinking about parametric curves. Because time, if you think t is time, the curve, then the parametric function, it just traces out the curve, right? It's like it's drawing the curve as time goes on. I can't call the parameters both time, right? I guess, I don't know, that'd be a weird, like maybe, that'd be one of those very confusing sci-fi movies that nobody really follows. You know, two different senses of time, right? That'd be a fun movie to try to make sense out of, but it doesn't really, it'd be extremely confusing. Okay. All right. Okay, so how do we create parameterizations in general? And it's a hard question. It's a tools for your toolbox kind of a deal. There is no single way to do it. There are multiple methods that work in different scenarios. The book does have a bunch of examples of parametric surfaces. My criticism of the book in this section is that they only show existing parameterizations and then help you interpret what surfaces they represent. And I claim this is backwards from what you need, right? If you're encountering some natural scenario where you're going to need to parameterize a surface, you don't get the parameterization to start with. You just start with some surface. You need to start with a surface and know how to create a parameterization, not how to assume a parameterization and then interpret what you were given. So anyway, all of my examples here are in the form of generating a parameterization. Here's my favorite method. It's called the graph parameterization. I hope that rings a bell. We've done graph parameterizations for curves in 2 dimensions. And remember the big trick when you're talking about curves in 2 dimensions, specifically if that curve is a graph, you let the parameter be the input variable. That was the big trick. Let the parameter be the input variable. Okay. So what we're going to have here is extremely analogous. Again, when you have a graph, right, such as I have in this equation right here, those are graphs. You let the parameters be the input variables. So the only difference is now it's plural. Right? Now there are 2 input variables that we let be the 2 parameters. Okay, so let's see how this works. I mean, in practice, how does this actually create a parameterization for us? Well, nothing to it. If you let your parameters be your that's the wrong color. If you let your parameterization, your parameters be your input variables, that gives you 2/3 of your parameterization right there. Position as a function of S and T. Well, the first 2 coordinates, easy functions of S and T, they just literally are those parameters S and T. Where do you get the third one from? Well, if S and T are X and Y, and if X and Y determine Z, then that immediately tells you how to find Z in terms of S and T. Does that make sense to everybody? Again, it's all follow your nose after you make this one initial, very important, very clever choice let your parameters be the input variables to the function whose graph you're looking at. Okay. All right. So strongly analogous. Now, again, it doesn't really matter which variables are playing what role. You'll notice here, for example, that I've got this is a kind of a graph. This is y is a function of x and z, instead of z being a function of x and y, and that's a little different, right? But whatever, alphabetical order doesn't mean anything mathematically, right? It's perfectly fine. And we can still follow the rule and let our input variables be our parameters. And given that, y has to be what it has to be. So same idea. Different roles being played by the different variables. Everybody good with that? Now you'll notice there was a little bit of a trick that I kind of glossed over at the beginning here. Let's go back and look at this. I wasn't actually in this question given y being a function of x and z. The question did not come quite in that form. The question came in the less clear form of we were looking at a surface with an equation. It didn't come as a graph. But keep in mind, just because it's not written as a graph doesn't mean that it can't be rewritten as a graph. So you always want to look out for these possibilities, and again, keeping in mind that it could be any one of the variables that you can solve for. So you can't solve for x and z here, but of course you can very easily solve for y, and then as previously discussed. What do you think? Everybody in? Okay. All right. One other variation. If you're in a different coordinate system, same deal. Just first write down the change of variables function. Just write down x, y, z equals, and then the formula in spherical coordinates. And then the same thing applies. Notice that I have here a graph, you might say. This is what I would call a spherical graph, because while I have not solved for one of the rectangular variables, I've solved for one of the spherical variables. Rho here is a function of phi and theta. A lot of people get uncomfortable when I say this is a function of phi and theta because they don't see the theta. That's a good thing, not a bad thing. This is just a really easy function of theta. Right? So that's fine, no problem. This is a function of phi and theta. So, having noticed that, then again, you just kind of plug in. I mean, I'll confess the plugging in process is a little different. But ultimately, I'm just plugging in what I had now into the conversion formulas. And again, we win, and we have a parameterization because we have position now as a function of two parameters. This time, the parameters are phi and theta. No law that says the parameters have to be called s and t. Right here, I'm using phi and theta. Okay. All right, moving along. Bad news, good news. We, being as we are a little low on time, and I'll remind you that, tough decisions and all that. This example is, I think, a cool example in a way. It's a nice example of how to use a technique that is powerful. We saw some examples of parametric curves where you can use vector algebra to turn hard problems into easy problems. You remember the one with the bicycle wheel and the reflector on the bicycle wheel, and it makes that weird shape. This is kind of a surface version of that in a way. But in terms of how often it comes up and how much you're going to be using it, this is a little obscure. So I am going to just remove this example. It's not really necessary as part of the course. So feel free to look at it if you like. As always, feel free to come ask me questions. As always, if you're interested, if you need a little help making sense out of it. But also, you're welcome to ignore it if you choose. Okay. All right. Now, this one is actually really useful. This comes up a lot. This is my take on a situation that comes up a lot. So what I'm going to call here creating a coordinate system sounds like a lot. It sounds like a challenge. It sounds really hard. It's actually surprisingly easy in a lot of scenarios. So keep in mind, when I say a coordinate system, I don't mean a new coordinate system for all of space. I just mean a coordinate system to describe location on the surface. So the surface itself will usually kind of suggest, what would be a natural way to describe, where you're located on the surface. So let's just see an example of this. Let's talk about this torus, which is the surface of a donut, basically. So this thing right here. How would you describe your location on this surface? And I don't know why I find this entertaining to imagine, instead of imagining a pastry, right? I like to imagine a gigantic space station, right? And the space station is shaped like a donut because if you shape it like that, and then if you get it rotating, the centrifugal force will create a kind of an artificial gravity. They've done this in some movies here and there, and it's perfectly reasonable that could work. Right? So if you had a gigantic space station shaped like this donut, how would you describe locations on that space station? Right? So here's what I think, and there are different ways to do it. I think there's a couple of angles that pretty naturally help you understand where you are. So, for example, this point right there, that is a rotation by some angle around the z-axis from a point in this, what you might call positive part of the xz plane, the x-positive part of the xz plane. This angle that I'm calling S here is what in other contexts we might call theta. And this is basically the cylindrical coordinate theta. But, we don't need to think of it in those terms. It's the point is I'm just going to call it S. This says how far do I kind of rotate around the outside circle, you might say, of the donut. Okay. All right. Now here's the other thing I'm going to need to know, though, if I want to identify what location I'm talking about. I'm going to zoom in a little bit. I am going to need to talk about this point that I'm rotating from, and that point, now that could be anywhere on this circle, and how would I describe where I am on that circle? Well, I think this angle right there, what I'm calling T here. Right? T equals 0 would be right there, and as T increases, it just kind of takes you around the circle. A pretty natural choice if you want to describe where you are in a circle. Angle, right? Vaguely suggestive of like polar coordinates. Okay, so with that noted, we have two coordinates set up, and that is actually a perfectly acceptable coordinate system. If you give me a T telling me how far to angle up, and then a S telling me how far to rotate around, that then gives me a well-defined location on my surface. And again, space station or donut, take your pick. Is that cool? There's one way to go. I could imagine other ways to go, but I think this is about the easiest you're going to find. Okay. So believe it or not, having chosen a coordinate system like this, we are kind of done. All that remains is really just kind of some geometry. So now you do need to make sure that you can do this geometry. Y'all have spent a lot of time learning trig and geometry and linear algebra, adding vectors and stuff like that. And that's really all that follows. I'm just going to walk you through and hit the highlights here, talking first about that point right there. I'm going to think of kind of like this, just to make it a little bit easier to look at, get rid of sort of the rest of the confusion in the picture. That point, I think it's pretty comfortable to say that that is this vector plus if I can get that thing, there we go, this vector. Right. Purple plus blue gives me that green. And I'm going to leave as a geometry exercise, geometry/trig exercise for y'all to think through, you know, where did I get these formulas for these two vectors? It's really just a matter of looking at the picture, thinking about the geometry of where this angle is, what that magnitude is, et cetera, and doing a little bit of trig. And there you go. And so this point that we're trying to describe, this thing I'm calling P, that point right there, is just that sum. That's the first step. That gives us this green point. Now, keep in mind what we're going to do with that green point is we're going to rotate around the z-axis. So that's our next goal. We have to figure out how do we describe a rotation around the z-axis. Well, Math219. Right, linear algebra, and again, you know, we've talked about this a bunch, and I've implored y'all on several occasions, make sure you're good with standard geometric linear transformations. So that's rotations, reflections, that kind of stuff. And in this case, rotations are a linear transformation. Linear transformations are represented by matrices, and the columns are the images of the standard basis vectors. So I want y'all to fill in the gaps on this. Think about how would you rotate, like so, how would you rotate the standard basis vectors around the z-axis, right, like I'm doing with my hand here. And when you rotate the standard basis vectors around the z-axis, these columns, I claim, are what you get. So make sure you can do that. In fact, I would encourage you to try to do this on your own first, and then check and see if you get the right answer, as opposed to trying just to reproduce what I already have. It's always easier to reproduce what someone else has done than to do it yourself. So give it a try. And at this point, it is all over. We have that P point that we did a little bit of geometry to find. We just talked about how to find this rotation, and the result is the point on the torus. And so it's kind of a weird formula for parameterization, but that's where you get it from. Everybody happy with that? Reminder, quick summary. It all started with choosing a coordinate system, right? Choosing just because of the geometry of the figure here, that look, there's kind of a roundness in this direction, right? And there's also kind of a roundness in that direction. That kind of suggests choosing two angles. And everything else that follows after you've made this decision to choose these angles as your coordinate system, everything else that follows is just geometry. This is what actually makes the parameterization possible. Okay. All right. Last one. Sometimes you can tweak what you already have. So let's start with an easy parameterization. Suppose you're interested in the unit sphere. Notice that this is a spherical graph. I have rho as a function of the other variables. An easy function, right? But nevertheless, I have a graph because rho is a function of the other variables. Play the graph parameterization game. You get that parameterization right there, which you can write out in coordinates if you prefer, like that. Okay, that's an easy one. Now here's where it gets challenging. Let's suppose you wanted to parameterize an ellipsoid. How would you parameterize this thing? And that's gonna be weird, right? I mean, you could actually technically solve for rho. It'd be not nice, but you could, right? So instead, here's what I'd like to do. Instead of trying to parameterize this ellipsoid sort of from first principles, right? Let's recognize that that ellipsoid and that sphere have a lot in common. They're really close to each other. In fact, the only difference, or let's say this differently. The only thing I have to do to a sphere to generate this ellipsoid is just stretch it. Right? I need to stretch by a factor of A in the x direction, a factor of B in the y direction, factor of C in the z direction, and that will turn this into that, right? Flashbacks to chapter 1. All right. Well, let's just kind of do that one step at a time. If I want to stretch in the x direction by a factor of A, I appeal to your geometric intuition. Stretching by a factor in the x direction just means I'm going to multiply those coordinates by that factor. So here we go. Let's see here. Let me clean up the thing. This x coordinate for the on the sphere, I can turn that into this x coordinate on the ellipsoid, just by, again, stretching by a factor of A. Right? I need those x coordinates to be A times as big, and I do that by literally multiplying by A. That literally makes them A times as big. That's all there is to it. Does that make sense? All right. Analogously, and you can probably see this coming, but analogously, if you want to stretch by a factor of B in the y direction, well, then you just need to introduce an extra factor multiplying those y coordinates by B. And it literally makes them B times bigger. So, okay. Likewise for the z. Okay, now here's an alternative way to go, different way of thinking about the same thing. You'll notice, in fact, that in this, in turning that equation into this equation, we talked about replacing x in the equation with x over a, right? And that accomplishes the stretch by a factor of A. Well, you can do that in the parameterization too, and you can see it right here. That x I could replace with x over A. Right, this is the same parameterization of the sphere, just written out in coordinates from what I already had. Literally replace x with x over A. That stretches by a factor of A as well. So students get confused at this point very often and say, well, wait a minute, how come you multiplied here, you divide here, you're claiming it's the same thing, but in one you multiplied and one you divided, what's that? That seems contradictory, right? But keep in mind, there's a difference between what you do. Let's see here. Let me, bear with me just a second. I'm going to scratch that off real quick. Let me remind you that this is XYZ. There's a difference between what you do to what X is versus what you do to where X is written, right? And in fact, even though in one case I divided, in one case I multiplied, I think you'll grant me these equations are in fact exactly the same. I mean, this is really morally the exact, I mean, as long as A isn't 0, these are totally equivalent equations. So it's just a question of how do you choose to think about it. If you want to think about it from a point of view of these are literally, this is the formula for the x coordinate, I'm going to multiply it by A, right? Or you can think of it more sort of algorithmically as I'm going to replace where the x was written. There are different perspectives on what is ultimately exactly the same thing. Okay. Everybody happy? All right. Yeah, so I've already made this complaint here. Again, the book's examples are, they don't help you find parameterizations. The book's examples helps you interpret parameterizations that you might be given. But I think in the real world you need to make parameterizations, and that's what we've been talking about here. Okay, moving along. Okay, this next page also, again, there's, tough choices, and sometimes we have time for things, sometimes we don't. What we have here on this page is a kind of a motivation / derivation of a formula that we're going to be computing stuff with, and we just don't really have quite enough time, I think, to be able to cover this. So y'all are absolved of everything that's on this page. You don't have to read this stuff. As usual, I think it's healthy, right? If you want to know where the formulas come from that we're about to talk about, this is the beginning of that development. So I'm going to basically punt on this page, and we're going to go to what that leads us to, which I'll talk us through. I'll give you the sort of the broad strokes here, and then we'll take it from there and do some computations. So, so here's the idea. We have a parametric surface. In this case, you see we have a sphere where position in space, position in space, my stylus is out again. All right, so this is a weird example. Okay, I'm going to have to use my finger because I lost my other stylus. Okay, I can just go with the finger. So, sphere where position in space is a function of our two parameters, and our two parameters are phi and theta. Right, so that's one of our spherical parameterizations, and the details of this formula, of course, we've already talked about. So I make the modest observation that if I were to move a little ways over in the phi direction, well, then that's going to move me on the sphere as well. And big surprise, it's going to move me in the phi direction, right? So keep in mind, phi is measured from straight up. Increasing phi means you're sort of going down a meridian line, right? And so that on the surface of the sphere would look something kind of like that. Now, likewise, I could go somewhat in the theta direction. And big surprise, that would move me on the sphere in the theta direction, right? I would go sort of around a latitude line. So putting those together, let's see, whoopsie. There we go. Putting those together, in fact, let me get rid of all of this mess. Putting those together, this little piece of area here, an amount of area in the phi theta plane, there is then correspondingly this little piece of area on the surface of the sphere. And y'all can probably see what's coming. We've done this kind of a thing in multiple previous contexts. Change of variables being our first example, where you have a world over here and then a function that pushes you into a different world over here, and the idea then is expressions on the right pull back to expressions on the left. It's just a matter of plugging in, right? And all you really need, other than literally just plugging in algebra, right? All you really need to be able to do a pullback is the stretching factor. So I just need to know by what factor does that area get stretched out to generate that area. So the way we're going to do that is by actually literally computing this blue area. And this little blue area is a parallelogram, and we have a formula for how to find the area of a parallelogram. The area of a parallelogram is the magnitude of the cross product of the two edge vectors. Now, these two edge vectors that I got from moving in the phi direction and the theta direction, a claim of what I have written here. This comes from the previous page. This is what I'm skipping in this case, but I am going to make a quick appeal. You'll notice that these look just like the formulas for the edge vectors that we wrote down when we did change of variables. It's very analogous. right? So you might find some satisfaction in that. Anyway, this is the formula for that area. And if you know the blue area and you want to relate that to the green area, then a little algebra turns that into this, which you see now explicitly is a multiple of that. And we have ourselves a stretching factor. You can see the stretching factor then right here. Our stretching factor is, this is an important formula to memorize. Your stretching factor, when you parameterize a surface, the stretching factor is the magnitude of the cross product of the partial derivatives of your parameterization. So we're going to make sure to know that formula. Okay.
Can you repeat that one more time? It's the magnitude.
Yep. Let's see here. Let me do like that. Here we go. So there it is. So you see it's the magnitude, right? The vector that we're taking the magnitude of right here is a cross product. The things we're taking a cross product of are partial derivatives, the two different partial derivatives of our parameterization. Yeah. Okay, now a little bit, before we go off and actually do an example here, I want to talk about notation and terminology a little bit. It ends up being really useful in ways that we're going to totally see in like just a few days. That the vector itself, not the magnitude, but just the vector whose magnitude we're talking about, this vector itself is actually going to be really useful in various ways. So this is worth having a name. We're going to call it capital N. It's a fairly, I don't want to say standard, but it's a very common choice of a notation. So that allows me then to rewrite the formula for the stretching factor. And I suppose I could call it magnitude of the cross product of xd and x theta, or xs and xt, whatever your two partials are. It's just very convenient and compact to call it magnitude of capital N. Very handy notation. We're going to be using that a lot. So make sure to remember henceforth that when I write down capital N, this is what I mean. All right. Now, what do we call this thing? This thing that I'm calling capital N, that I'm writing as capital N. First, I want to observe that that's a normal vector. These two edge vectors here are tangent vectors. These two vectors that I'm doing the cross product of are in those same directions. So these are tangent vectors, and the cross product of two tangent vectors is going to be a normal vector. So I think that's a pretty reasonable thing. This is a normal vector. Now, it's not a unit normal vector, but the magnitude does matter because it is, very importantly, capital N is explicitly this formula. The magnitude needs to be whatever it is. And notice that the specifics of this come from the parameterization. Right? The whole formula for this thing, I start with the parameterization x, and then I do stuff to it. Right? So because it comes from the parameterization, I like to call this the parametrized normal vector. And that's the terminology I'm going to be using. I think that makes sense for as I just explained. Now, heads up, the book prefers instead of calling this the parametrized normal vector, the book calls it the standard normal vector. This is uncomfortable for me. Think about it. Standard kind of suggests something intrinsic to the surface, but this isn't. This depends on the parameterization. You can see it right here. And by the way, it really depends on the parameterization. If you choose a different parameterization, you will get a different parameterized normal vector. So to me, the word standard suggests too much uniformity that just isn't there. Right? There's a bunch of different parameterized normal vectors, one for each parameterization. And I just think it would be really weird to have a bunch of different standards. I think that's what standard means. So anyway, I don't care for this terminology. Heads up, it's in the book. I'm not going to use it. Okay. All right, let's see how we do it. Oh, gosh, we're short on time. Heck. I think what I'd better do is just go ahead and draw the line right here. We will call it a week, and see y'all on Monday. Have a good weekend. And don't forget about attendance if you weren't here when I did it earlier.